Hi, everybody. My name is Alvin Leung, and I lead growth and marketing at Vatical, the creators of TypeDB. I want to thank everybody for being able to attend our talk today on type theory as the unifying foundation for modern databases. Today, I'm pleased to be able to introduce our speaker, Dr. Christoph Dorn, or Christoph as we call him in the office, who will be giving our talk. By way of introduction, before joining Vatical, Christoph led cutting-edge research in theoretical computer science and mathematics at the University of Oxford, where he had also previously completed his PhD in computer science in 2019. His work in the areas of higher dimensional algebra and computable geometry, and he also co-wrote a book on mathematical foundations for a synthesis of these two subjects. Christoph has been working closely following the movement of type-theoretic databases for the past several years and shares our vision at Vatical to bring theory and practice together to build the next generation framework for modern database applications. We're excited to have him here to give this talk today, and I'd like to invite him onto the stage.
Thank you very much, Alvin, for the kind introduction. I'm very excited to give this first lecture in our TypeDB Fundamentals lecture series, and we'll also say a bit more about the upcoming lectures later in the talk. In today's talk, I want to talk about some of the theoretical roots of a larger vision that we're pursuing here at Vatical, which is to build a unifying foundation for the modern database. And as the title of the talk says, this will be firmly rooted in the modern theory of types. But actually, before getting into any theory, I wanted to get us started with a brief recap of the status quo of the database field, in particular highlighting some of the common issues that contemporary database languages still face. On one hand, nowadays there are many database paradigms for us to choose from. We can work with relational databases, with graph databases, document databases, triple store and RDF, and so on. But on the other hand, all of these share also many commonly known problems. First and foremost, this concerns mismatches between conceptual level modeling and logical level modeling. So when there's a mismatch between how you think about your data organization conceptually and how your data is actually organized in your database. And prominent examples include, for instance, the object relational mismatch, issues when working with reified relations or multivariate attributes, and so on. And this issue leads to unnecessarily complex database query code. So for instance, here I'm showing a SQL query which distributes fields of a single object across many different tables. And the root of the issue is that these existing paradigms really lack support for ubiquitous features that we find in data. So for instance, type polymorphism, but also interconnectedness and interdependencies in data. Second issue I want to highlight is that these current paradigms are not built to enable easy system extensibility and maintainability. So we often have to write long imperative queries where at multiple steps we need to supply hard-coded information about our types, and that makes these queries brittle and sensitive to changes of the underlying data layout. And the cause here is that existing paradigms don't provide a way of writing composable and generic queries instead. So these could then be reused in a much more robust way. And finally, there's the issue of data integrity. Simply speaking, if you don't have a sufficiently expressive schema to express the dependencies in your data, then you also cannot possibly validate your data meaningfully. So for instance, in graph databases, there's generally no facility, no way of ensuring that relations run between nodes in a sensible way. So specific relation types might only run between specific nodes, and there's no way of validating that. This also affects data redundancies, which often need to be carefully and manually synced and maintained so that integrity is not violated. This is just meant to be a very, very fast and brief overview of some of the common database pain points. It somewhat provides motivation to where we come from, why we embarked on this journey. But really, this talk is not going to be about details on these database pain points. For details, instead, you should attend our next lecture, Why We Need a Polymorphic Database, which will be given by James. Today, instead, I want to embark with you on a much more theory-driven journey. And the goal will be to really understand this deeper shift of paradigm in databases that we're envisioning. And this starts with the realization that, of course, existing database paradigms are also built on theoretical foundations. And these include domain-specific mathematical ideas like the theory of relations, the theory of graphs, trees, and so on. And these choices of theoretical foundation mean that the paradigms work well as long as your data adheres to a domain-specific shape. But the moment you go beyond that, you precisely run into the issues that I mentioned earlier already, like lots of data features cannot be expressed natively, and these paradigms are not natively built for the composability and extensibility needs of modern system. And moreover, they're also very bad at interoperating between one another. So to resolve this, we need to somewhat start from scratch. We need to rethink foundations of the modern database from first principles. And of course, this starts with rethinking the theory behind our database. In modern mathematics, there is now a general theory of composable structure. It's the foundational theory of types, type-theoretic mathematics. So this is a natural starting point for us to take inspiration for answering this question. Let me briefly get ahead of myself a few steps and talk about TypeDB, which is the database or the database ecosystem that we've built precisely based on this mission. So TypeDB lives at the intersection of classical database ideas, but also type theory and machine reasoning. And it comes with a truly type-theoretic query language. So we'll really see how the mathematical theory matches the expressions in our query language in this talk. It also comes with conceptual data modeling to provide very rich semantic context, which is further enhanced with type polymorphism. It has an inference engine that automates a lot of work for the user under the hood, and a machine reasoning engine that allows you to integrate your application logic very, very easily into your database. Let me just briefly emphasize this data model that we're talking about here. You should really not think of it as similar to relational data model, graph model, or document model, but rather as a joint generalization of. So let's see how type theory comes into play here, because it really powers all four of these features that I've just mentioned. So let's start with the rise of type theory and the modernization of math. Classically, and this was also the original inspiration for relational algebra, classically mathematicians thought of mathematical structures as being based on two ingredients. On one hand, that's sets, and on the other hand, that's relations, which are also called predicates, and governed by predicate logic. Let's make this example a bit more tangible. So let's, for instance, consider the set of persons. So P is a member of the set of persons. And then a relation could, for instance, be a relation of marriages. And the marriage of P1 and P2 gives you a truth value. So either P1 and P2 are married or they're not married. Now, this way of thinking about mathematical structure was hugely inspirational for a lot of 20th century mathematics, definitely provided inspiration for relational algebra, but also for logic programming languages like Prolog, Datalog, and so on. But it was also extremely non-practical. It turned out to be extremely non-practical. So modeling everything in sets and relations was not practical for the working mathematician. And I think you probably don't need to be a mathematician to sympathize with that. Many of us know that trying to model everything in relations can be quite restrictive. Thankfully, mathematics moved on. Mathematics moved on to composable systems. And in this more modern perspective, there's really just one ingredient. So everything every mathematical structure is a type. So for instance, there's now a type of person, in our earlier example, but also a type of marriages. So the type of marriages between P1 and P2 would hold as objects or as instances marriages between P1 and P2. And now there can be 0 marriages, there can be 1 marriage, but there can also be multiple marriages between 1 and P2. This, at first glance, might seem like a very small shift of perspective, but unifying all these structures as types really has very powerful repercussions. So facts like marriage previously was a fact becomes data itself. And now this data can be explicitly referenced. So for instance, we can now ask for our marriage M, what is the date of M? And the fact that we can have dependencies of types on other terms and of terms on other terms also means that we have a composable theory. These dependencies can be composed. And has been hugely successful. Just in recent years, there have been still many celebrated successes, and it's de facto the practical foundation of modern mathematics. In fact, Paul Taylor in 1999 wrote a book titled Practical Foundation of Mathematics. We have it in our office, and this book was about type theory. And I would say that if he had written this book 30 years earlier, before Court's relational algebra, probably databases today would look very, very different. But instead of ruminating about potential mistakes in our past, let's look forward and ask the question, can we use these new practical foundations of mathematics to also build practical foundations of databases? And this is not a far-fetched question, because types are really just declarative descriptions of data domains. And as such, they very naturally can be thought of as declarative queries, like they describe the domain of data that we like to retrieve. And that brings us to the question of how to build a type-theoretic query language. I don't want to assume that everyone is familiar with type theory, so here's a little crash course in type theory, which is not tailored for mathematicians, but you just need to speak English. Let's start with a definition of what a type precisely is, and I want to give the following definition. A type is a description of a domain that a variable can range over. So this is a very general definition. In particular, it applies both to examples in mathematics and programming languages, but also in natural language. So on the left-hand side, we have the classics, like the type of integers, saying that a variable x is an integer means that x can range over the domain of integral numbers. Another all-time favorite, saying that y is a string, means that the variable y can range over the domains of all strings. Here's a slightly more mathematically inclined example. We say z is a factor of x, and that as well describes the domain that z can range over. But now the description is dependent on a variable. And accordingly, we would talk of a dependent type here. And then you can initialize that variable to a specific term, a specific value term, and then let's say x equals 26. Z would be described as ranging over the domain of factors of 26. But we also have examples in natural language. We've already seen one. For instance, person is a completely fine description of a domain. Saying that P is a person means that the variable P can range over the domain of persons. Another one is N is a name of a person P. So this is an example of dependent type. And the example that we've seen earlier of marriages is also dependent type, saying M is a variable in the type of marriages between persons, P1 and P2, describes the domain that M can range over. Now in type theory, you don't need to consider types in isolation. Like you can combine types to get more interesting descriptions of data domains. And that's similar to how predicate logic works. So in particular, you do have logical ands and ors. These are pretty easy to represent in type theory as well. But type theory is much more general than that. And crucial to the generality is precisely the ability to have types to depend on other types. So here's an example. So simple logical AND would be something like X is a person and Y is a city. And the type theorist would call this a pair type. But with type dependencies, we could also have a combined statement that reads X is a person and Y is a name of X. So here the description of the second variable references the variable in the first part of the description. And the type theorist would talk about the dependent pair type. And we care about these dependent pair types a lot, and they're particularly nice because they can compose. So let me give an example of that. We've seen all of these types before. We've seen the type of person, so that P1 and P2 be variables in the type of person, M is a marriage of P1 and P2, and let's say D is a date of M. Then these compose into a single combined type that reads D is a date of a marriage M of persons P1 and P2. So here we have composed these type dependencies in a meaningful way. And type theorists can actually write this down formally mathematically. So there are actually dependently typed programming languages. Acta is one of them. So I'm using a code example here that's similar to Acta as a dependently typed programming language. And this would be how you write the type that we just talked about. So the date of marriages of persons. We think that we can write this, we can do slightly better. So TypeQL, or query language, can also express complex and combined types like this. But we would write the same dependent type as follows. So here's a TypeQL pattern that expresses the same type. We would write P1 is a person, P2 is a person, M of P1 and P2 is a marriage, and M has date D. So this is much more readable. But it's important to keep in mind that it has this formal theoretical interpretation of a type. And as such, it's a domain of data. And maybe if we have a database which records persons, marriages, dates, and whatnot, then we can use a declarative description of a domain of data like this to write a query. And this is where the type-theoretic querying comes in. So this is how, on one hand, we have type 3, and on the other hand, we have declarative querying. So composite dependent types are queries for us. In reality, so the theory is very elegant here, of course, but in practice, we cannot really expect our users to learn dependent type theory, unfortunately. So TypeQL needs to do, and TypeDB needs to do much more under the hood than plain type-theoretic languages. We need to make the life of our users much easier, of course. And this brings us to the conceptual data model that underlies TypeDB, enhanced with type polymorphism, as we will see. So let's revisit the query that we just looked at, slight variation thereof. So this query now reads, NYC is a city, has name New York, Dest is a city, F from NYC to Dest is a flight, F has duration less than 600, where you can think about maybe 600 minutes or 10 hours. What this query does is intuitively very clear. I mean, the query language almost reads like natural language. So what we're querying for here is a city Dest, which can be reached by flight F from New York City, and the flight must have duration less than 10 hours. But often a user either does not want or actually cannot supply all this information, all this type information. So maybe a user does not want to just consider flights, or maybe a user does not want to just restrict our destinations to cities. So just omitting this type of information from our query still leads to a valid TypeQL query. So NYC is a city, has name New York, F from NYC to Dest, F has duration less than 600. Still a valid TypeQL query. But this now begs the question, how can we interpret this? So how can we possibly know what the user wants? And this is where the semantic context comes in. So our database has semantic context to interpret these queries. There's a database schema, an expressive database schema, which we can then use to do type inference and type validation on the query written by the user. And This is not based on abstract type-theoretic mathematics, thankfully, but instead, and this is one of the core innovations of TypeDB, it's based on an intuitive conceptual data model. Let's see how that works. So how we go from a conceptual data model, conceptual schema to type theory. Well, classical conceptual modeling thinks of natural language as categorized into three categories broadly. So on one hand, there are nouns, like a person. Then there are verbs connecting nouns, like a person marries another person. And then there are adjectives or adverbs, like a person marries a person today. So adjectives or adverbs qualify nouns or verbs. And in conceptual modeling, we abstract this a bit. We talk about entities, person is an entity, relations, marriage is a relation, and attributes. So a date of a marriage, for instance, would be an attribute of that marriage. But these examples are examples that we've already seen. So we already know how to think about this in a type-theoretic way. So we'll add a third column here, which is the type-theoretic perspective on conceptual modeling. Entity types, of course, just types without dependencies, like a person. Whereas relation types and attribute types are types with dependencies. So a marriage of P1 and P2 depends on P1 and P2. So it's a dependent type. And the difference between attributes and relations here is that relation types contain abstract objects referred to only by some object identifier, some pointer maybe, whereas attributes are types. Attribute types are types which contain concrete value that have algebraic structure like integers, strings, and so on. So TypeDB exploits this type-theoretic perspective on intuitive conceptual data modeling. Let's see how this works in practice. So this is our type-theoretic query from earlier. New York City is a city, has name New York, and we're looking from flights from New York to some destination that take less than 10 hours. How could we give our database a conceptual schema, conceptual data model to interpret this query? Well, let's go through it line by line and reverse engineer possible schema. Of course, there are many possibilities, but we'll showcase a simple one here. So the first line starts with NYC is a city. So in particular, city must be a type, and it must be an entity type because there's no dependency on any other variable. But then the first line also reads, NYC has name New York. So there must be another type, an attribute type, a name, and it must be of value string, since New York is a string. And now we have a dependency. We have not only just a name New York in isolation, we have that the city has the name New York. So it's a name of a city. And this dependency we also record as semantic context. We say cities can have names. And we write this in our schema by the line city owns name. Let's look at the next line. So F, remember, was some abstract mode of transport, not necessarily a flight. So let's introduce a type for F. Let's say it's a transport type. This must be a relation because it's dependent on two variables. It's dependent on NYC. It's a transport from a city to a city, or maybe something else. So we must introduce these dependencies as well. And in TypeQL, we have named abstractions, which we call role types, which provide a further level of generality, as we'll talk about in a second. And we record these for transport as follows. We say transport relates from a from role and transport relates a to role. And now we also need the context that we can have transport from cities. So we add this by saying that city plays the role of having transport from it and plays the role of having transport to it. So this provides the context for the second line. And then in the final line, well, we must have an attribute. So we introduce an attribute type duration. And this attribute in particular depends on transport. We have duration of F. F is a transport. So we add the context that transport owns duration. Forgot to mention duration here in this example is of value integer or long. So now on this slide, you have the two main components of the type-theoretic foundations in one slide. On one hand, it's the type-theoretic query language, which we've seen is is directly related to a dependent type theory. And on the other hand, we have the type-theoretic conceptual schema that gives the semantic context, which then allows us to interpret the query. But there's more. By virtue of working in type-theoretic foundations, we essentially get type polymorphism for free, or it very naturally integrates into this picture. And I want to talk about three common forms of polymorphism, starting with inheritance polymorphism. So inheritance, maybe the most common form, lets us specify type, or lets us think of types as inheriting the specification of a parent type. And this allows a hierarchical organization of our semantic context or of our conceptual schema. Let's see an example of this. So we're starting from our previous schema. We have a name attribute, we have the city type, which owns the name attribute, we have a transport relation, and city plays the roles from transport to and transport from. We could now specialize the type of transport. We could introduce a new type, flight, which subtypes the type of transport. And immediately, flight will inherit the full specification of transport. Transports have durations, and flights too will have durations. Transports relate the roles of going from something and to something, and the same will apply to flights. But we can also give further, more specialized behavior to the type flight now. So for instance, we can say it owns flight numbers, where flight number is some string attribute. So this is a powerful way powerful and very natural way of organizing the schema. Equally powerful is the next form of polymorphism, interface polymorphism, which is used to abstract the types that other types depend on. And we've already seen examples of this. So instead of specifying that a type depends on a specific other type, you just say that in order to depend on another type, this other type needs to have a capability. That's the interface, if you want. Let's see an example of this. So going back to our schema, we've seen that we had a name type, a name attribute, and a city entity, and that owned the name attribute. But there could be another entity type as well, say a person entity type that also owns the name attribute. So having a name is less a specification of a type, it's more of a capability that a type can have. And the same applies to dependencies on other types by relations. So for instance, we've seen that the relation type transport could go between cities. So it could be transport between from city 1 to city 2. And we specified that by saying city plays the role of transport from it and transport to it. But there could be other types that also have this capability. So an airport, for instance, could be an entity type, which also plays the role of having transport from it and transport to it. So again, this gives you a way of very neatly organizing the data. And it's very, very close to how data is structured in the real world. And the final form of polymorphism I want to touch on is parametric polymorphism. Parametric polymorphism in general defines generic functionality by using variabilized types. And for us, in the context of databases, that enables semantically generic queries, writing semantically generic queries. It's a bit different from inheritance and interface polymorphism because this is not at the level of specifying the schema. This is at the level of actually implementing database functionality. So our example here is a simple match delete query, which deletes data from our database, something that we haven't seen yet, but it's just as easy to read. So let's read this query. Match something owns name. Object is something, is a something. Object has name. Delete object is a something. So in this query, something is some type that owns name. So it's a type. So we can have names of something. Object is an instance of the type something. Object has a name. And if it has a name associated to it, then we delete it from the type something. This query is completely agnostic to what the type something actually is and the name ownerships you have defined in the schema. So it's maximally semantically generic, if you want, with respect to name ownerships. There's one final key component to TypeDB, and that's our reasoning engine. And our reasoning engine too has theoretical roots in type theory. So we talked about dependent pair types earlier. Type theorists also call them sigma types. There's another type of dependent type, which is dependent function type. And for dependent function types, we also see a role in modern database foundations. Namely, we regard functions, dependent functions, or rather first-order dependent functions, as a way to infer data logically from source data. Let's see how this works in an example. So these function types in TypeDB are called rules. So here's a rule called possible two-leg flight, and it reads as follows. When flight 1 from city 1 to city 2 is a flight, has arrival time 1. Flight 2 from city 2 to city 3 is a flight, has departure time 2. Time 2 is greater than time 1 plus 30, so you can think of 30 minutes. Then there is a two-leg connection with leg 1 being flight 1 and leg 2 being flight 2. So this is very similar to TypeQL data retrieval syntax, TypeQL pattern syntax. So again, it's close to natural language. It's intuitively clear what this rule should be doing. But of course, under the hood, there's more going on. So to really make this work, we need to build a reasoning engine. And that's what we've done in TypeDB. It's not going to be the topic of today's talk. But the reasoning engine evaluates our rules at query time so that we always get an up-to-date data based on the logic in our database application. And a central gain, a key gain that we get from allowing these more complex forms of logic is that we get very fine-grained control how we infer data from our source, from the source data in our database. And in fact, much less powerful ways of this mechanism are present in almost all database paradigms. So for instance, in relational databases, we have views that can be generated from our source tables. In graph database, we work with paths, which are generated from the nodes and edges in our database. And document databases, we have, for instance, aggregates. And this brings us to the final part, the result of our efforts of putting type theory to use to build a modern foundation for databases, namely the unification of existing paradigms. So I briefly want to talk about how you can think about simple ideas from other paradigms in TypeDB, in the type-theoretic, in the polymorphic conceptual data model. Let's start with relational databases. So, well, in a relational database, you have tables, you have foreign keys, and each table has columns that might contain values or foreign keys. Let's consider columns here that contain values. Migrating to the conceptual model is really not difficult, precisely because the conceptual model lives somehow at a meta level, above more specialized models. So what we would do is at first glance, we would take tables to be entity types. Foreign keys are relations between tables, and columns with a value will become our attribute types. Of course, the experienced SQL engineer will say, well, I don't really think that modeling all my tables as entity types is a good idea. Some of them might be relations. And that's true. In this case, you would speak of join tables or associative entities. But in the relational model, we lose the semantic context. So in a way, the relational model flattens the dependencies between concepts. So without further context, we can actually not know whether a table was meant to be an entity type or relation type. Disregarding this technical issue for now, and I should say that we're going to dive deeper into that topic, how to think in the conceptual data model of TypeDB. We're going to dive deeper into that topic in upcoming lectures as well. So here I only want to outline it briefly. So let's consider a simple example. So here would be how you would model a simple relational schema in the conceptual schema of TypeDB. This is a schema that has two tables, a table of student, which for instance has a column subject of study, it has another column start date, and then it has a foreign key which links a student to its supervisor. Supervisor will be a professor. So professor as a table 2 is an entity type, has various columns, it has a name, it has a name column, it has the number of students as a column, it has maybe a Boolean column, whether or not the professor takes new PhD students. And then the foreign key of students in the table of professor will be modeled by a relation. So there's a supervision relation that relates students and professors. And well, students play the role of the supervisee, and professors will play the role of the supervisor. So it's a very, very simplistic example here, but I think it gets the idea across. Let's briefly look at a second example. Let's look at graph databases. Again, translating into the conceptual model is pretty straightforward here. So we can think of our different types of nodes as entity types. We can think of edge types as the relation types in our schema. And properties of either nodes or edges would be modeled by attribute types. Importantly, path composition now becomes a question of logic. So the way we want to compose edges is often very specific, and this can be modeled using logic in TypeDB. And generally, it's much more expressive, as we've seen in an early example, than the graph approach, which has little control over the logic used to compose paths. Here's a simple example building on our earlier schema. So for instance, we could consider a simple graph of city nodes with flights between those cities. Cities could have a name property, so each city has a name. Flights could have a departure time and arrival time property, and they relate departure cities and arrival cities. So there are edges that go between cities, directed edges. And then we could think about the type of logic that we need from this graph. We could think about two-legged flights or multi-legged flights, and define in precise terms the logic that we want to get out of our graph. I'm going over this rather quickly, but similar observations apply to other data models simply because the approach of conceptual modeling is so general. So it's really easy to work with the conceptual modeling, and it's really intuitive. So let's take stock. Let's go back to the very beginning of this presentation where I pointed out 3 problems that were the status quo. Let's see where we arrived now with our new foundation for databases. So the first problem I had pointed out was the mismatch between the conceptual level and the logical level modeling. It's a bit of a triviality to say that one is solved simply by making the conceptual level model our actual database model, and further enhancing with type polymorphism to really get a detailed and highly expressive schema that can model all types of data features. The second point was the lack of system extensibility and maintainability. And we also saw how that was solved, namely by a type-theoretic query language that was fully declarative and that allowed the user to omit the parts that they maybe didn't know or didn't want to specify, and then having a type inference engine on top of that essentially, based on the schema you have, infers what this query and interprets what this query is meant to do. And the final point was the data integrity, and that is resolved by a combination of type inference and machine reasoning. So we can always keep our data fresh. We don't need data redundancies. Instead, we can encode that using our application logic, and our type inference engine will actually check that the data we insert and the data operations we perform on our database are semantically valid. So it's really an elegant way to kill multiple points with one stone. There's much more to talk about. Let me give a brief overview, a brief high-level summary of what's to come and what we've seen here. Well, this was an introduction to TypeDB, to the theory underlying TypeDB, and TypeDB is a database that implements the type-theoretic polymorphic paradigm. We've seen that this gives key advantages to TypeDB that many current database paradigms cannot achieve by design. And I also want to say that TypeDB is a young database, it's a fast-evolving ecosystem. So yeah, we're on this journey, and we are very grateful that you're joining us on the journey. And yeah, we're looking forward to your input, to your feedback, to your questions. And we also hope that this was interesting enough for you that you will attend our upcoming lectures. They're shown on the slide here, and the registration is available under the link typedb.com/lectures. Thank you very much for your attention. I think Alvin is going to take over at this point.
All right. Well, thank you everyone for taking the time to listen to this lecture on type theory and what it means to modern databases. If you're interested in additional resources for TypeDB, I want to point you to three links that we have on the slide. The first one is we actually have a learning center at typedb.com/learn. This is an excellent portal for all the different resources you can go to refer to all things TypeDB and type theory. In fact, Christoph wrote an excellent article that breaks down in a little more detail, even more detail, the intersection of type theory, the application to databases, a deeper compare and contrast to what relational algebra and type theory actually means the foundation of mathematics, and therefore what it means to databases in general. I do encourage you to check that out. In addition to that, there's also links to the next lectures in our series as well too, as this is only part one of a 4-part series of lectures related to TypeDB, polymorphism, and type theory. So you can register there. If you're interested in getting more hands-on with TypeDB and installing it and trying it, I encourage you to check out our download section at typedb.com/deploy. Here you will have the option to download TypeDB, our core technology, on test out on your server as well too, in addition to some of the other deployment options we have. Finally, I'd like to also share that we are in the process of putting together a hosted offering of TypeDB. We are looking to launch that at the end of this year, and our waitlist is currently open for that as well too. So you can go to cloud.typedb.com to join our waitlist, and we will notify you once our TypeDB cloud offering is available. This is a version of TypeDB that we run in our data centers. We manage all the DevOps, the maintenance, the availability, all the things that just go into keeping a database up and running. You don't have to worry about that. Focus on building applications on TypeDB. All right, so this brings our presentation to a close. And we do encourage you to join our Discord channel at typedb.com/discord. Thank you and have a great day.